So in this question, we've been asked to evaluate the local minima, local maxima, and the saddle point of our function f of x comma y, which is equals to 8 plus 2x cubed plus 2y cubed minus 6xy. So there are steps in which we have to follow in order to calculate our different values. So the first thing we need to do is to compute our partial derivatives. We'll compute our partial derivatives. The second thing is we have to find the critical values. Find the critical values. And we find the critical values by equating our partial derivatives to 0. The third thing we need to do is to look for the second derivative. Look for the second derivatives. The second derivative and the mixed derivative. Very important. And the mixed derivative. The next step is we have to evaluate the Hessian determinant. The Hessian determinant. Then we compare the Hessian determinant. We compare the Hessian determinant to 0. I'll just call it Hessian determinant to 0. To 0. Pretty much, right? There are going to be some conditions where we're going to look at the end when comparing this Hessian determinant to know which of the points are the local minima, local maxima, and all of that, right? So for now, let's just follow these steps diligently. So the first thing we need to do is to compute a partial derivative. This is by far the easiest step because in almost all the videos we have been computing partial derivatives. So it's very easy here. What we have to do is to look for the partial derivative of our function with respect to x. We look for the partial derivative of our function with respect to y, and at the end add that because we're dealing with multivariable calculus, and in this case we have two variables. So our partial derivative of our function with respect to x, this is simple, it's a polynomial function. This will simply be, with respect to x will be 0, differentiating 8 with respect to x will be 0, plus differentiating 2x cubed with respect to x will be 2 multiplied by 3x squared plus 0 plus, again, negative 6xy. It's a product, right, of two functions, so I have to keep of two variables, right, so we have to keep one constant, we differentiate the other. So in this case we're differentiating with respect to x, so we have to keep minus 6y constant, and when we differentiate x we have 1. Now if you notice that if we keep y minus 6y constant and we differentiate x, this is just going to be 0, and we differentiate y, it's going to be 0. So if we simplify, we're going to have 6x squared minus 6y. That's it. So we'll do the same thing, right? But in this case, in the second case, we're differentiating with respect to y. In the second case, we're differentiating with respect to y. So the first thing, when we differentiate 8, we're going to have 0. When we differentiate 2x cubed with respect to y, we'll have 0. Plus, if we differentiate 2y cubed with respect to y, we're going to have 2. We bring down the power, we copy the same function, we reduce the power by 1. You can always say that to remember the formula. That's actually the chain rule. Now, the next step is we do the same for our product, because negative 6xy is a product. So we have to keep 6 and minus 6x constant. When we differentiate y with respect to y, we have 1. So this will just simply be 6y squared minus 6x. So that's our partial derivatives. So we've actually completed the first step. So the next thing is to calculate our critical values. And to calculate our critical values, we simply need to equate our partial derivatives to 0. So we know that 6x minus 6y is equal to 0. This implies that x squared should be equal to y. The second partial derivative, 6y squared minus 6x is equal to 0, which implies that y squared equal to x is y squared is equal to x. That's going to be our second equation. So we solve these two simultaneously. We can simply substitute equation 1 in equation 2. We're going to have y, but we know that y is x squared, so x squared, all that squared will simply be x, which implies that x to the power 4 minus x will be 0, which implies that x into x cubed minus 1 is 0, right? And this implies that x is either 0 or x cubed minus 1 is also 0. So here we can already identify that one of the solution is x equal to 1. Now there are two other complex solutions. When I talk of complex solution, meaning that the solutions exist but in the complex domain, right? And we can break this down to be x cubed minus 1 to be x, I think x minus 1 multiplied by x squared plus x plus 1. If you expand this, you're going to have this, and this is actually a complex quadratic equation with complex roots. So this is just out of our domain. Our main focus is this. So our critical point so our critical point is actually 0 0 1 1. We're going to see why. Now those are the critical points, right? From x, those are the critical points, those are the critical values, sorry, for the x coordinate. So now we're going to calculate the critical points, because a point is a coordinate. From the above equations, we saw that we had x to be equal to, we had x to be y squared and y squared to be x. So if we know that x is 0, y will simply be 0 by substituting it here, right? And same thing with 1. If x is 1, y will simply be 1. If x is 1, y will simply be 1, because 1 squared is 1. So therefore critical points will be 0 0 1 1. Very important. So we are done with that. The next thing we need to do is to look for our second derivative and the mixed derivative. Now what is our second derivative? Our second derivative is just like the derivative of our first derivative, the partial derivative of our first derivative, which is something like this, right? And it generally usually written as d squared f all over dx squared. And the same thing with y will be with respect to y, right? Which is usually d squared f all over dy squared. And our mixed partial derivative is usually d squared f, right? d squared f all over dx dy. And basically what we need to do is just simply take either df, right, with our function of our function df with respect to y, right? So this will, if we look at it critically, this is same as this, and you can always reverse it. You can always reverse it, because you can consider the derivative with respect to y, right, then of our function with respect to x. So that's it. Just have to pay attention to this. So this is what we're going to compute. So I had to reduce the screen in order to accommodate everything. So our next step is to just evaluate that. So to evaluate that, we're going to start with the first one, our partial derivative of our function with respect to x. So it will be the partial derivative of our partial derivative with respect to x. We saw that the result was 6x squared minus 6y, and simply this result will be, with respect to x, will simply be 12x. I'm not going into details. I'm sure we can understand, because I explained earlier, and in order to save time. So this is a partial derivative with respect to y. In this case, we had 6y squared minus 6x, and this will simply be 12y. I hope we're able to follow up. And the next one is simply our partial derivative of our function, right, with respect to, okay, so now our next one is, so in this case, and our mixed partial derivative will be of our function in terms of y. We saw that the partial derivative in terms of y was 6y squared minus 6x, and this is simply be minus 6, right? So having this in mind is extremely important to calculate our next step. So looking for the second derivative and the derivative, we're done, right? We're done with that step. So the next one is to evaluate the Hessian determinant. So what's really the Hessian determinant? So the Hessian determinant is simply a formula that shows the relationship between our second derivatives, our second partial derivatives, with our mixed partial derivatives. So the formula is something like our partial derivative with respect to x and our partial derivative with respect to y minus our partial derivatives with respect to x and y and x order squared. We already evaluated all of that above, so we just need to substitute here. So our Hessian determinant for the first one was 12x multiplied by 12y minus 6. So as simple as that, once we have this value, so we are going to evaluate it at the critical points that we saw above, right? And then we compare this with like some standard conditions. So if we use the first point, we're going to see that our Hessian determinant for the first point is simply putting 0 0 here will simply be minus 6. And now for the second point, putting 1 1 will be 144 minus 6, which will be, let's calculate that, 138. So that's the solution. So now we're getting close to our result. As I mentioned earlier, there are some conditions we need to look at, and the conditions are, if, I think I need to change the color, if our Hessian determinant is greater than 0 and our first derivative or our second partial derivative is greater than 0, then we are going to have a local minima. Now notice that when we're talking of greater than 0, we talk of minima instead, whereas greater indicates greater than or something bigger. So just have that in your mind. And also, if the determinant is greater than 0 and f of x is less than 0, then we have a local maxima. And if d is less than 0, just d less than 0, and we don't have any condition for our mixed partial derivative, then okay, so if we look at our mixed partial derivative, we see here that mixed partial derivative gave us -6, which was less than, that doesn't really matter, but once d is less than 0, then we are going to have a saddle point, and if d is equal to 0, it's unconclusive. So those are some conditions you just need to know. And yeah, with that said, we just have to compare, and doing our comparison, we're going to see that the point is 0, 0. It's our, looking at the comparison, the point, we saw that our d was greater than 0, right, for the first case. For the first case, we had -6, which is less than 0, right? Therefore, we can just conclude that the point 0, 0 is the saddle point. We already saw that our Hessian determinant is greater than 0, right, for the second point. So what we need to look for is what the value will be for our mixed partial derivative at this point. So if we look at our mixed partial derivative, we see that the mixed partial derivative with respect to x is 12x, and if we insert like our point 0, we're going to have simply, if we insert 0, we're going to have okay. So I just realized a mistake somewhere. So there's this square that we missed, and when we do the actual calculation, is actually 108, right? But that doesn't really matter much. So first thing, we know that our determinant in that case is greater than 0. So we can safely conclude that for sure the point 0, 0 is the saddle point. Now the point 1, 1, right, we cannot conclude. So for our Hessian determinant for the second part, we have to insert this in our Hessian formula, and inserting that in this Hessian formula, we are going to see that we have the 0.11, and our second derivative with respect to x was 12x, and the second one was 12y. So 12x multiplied by 12x multiplied by 12y, which is 12 multiplied by 12 minus 6 squared. So this is 144 minus 6 squared, 36. For sure we can do this calculation, right? And once you do the calculation, you're going to see that the result is definitely greater than 0. You don't need to even do the calculation. Once you know that it's greater than 0, right, what we are here, minima, we are at this point. Therefore the point 1, 1 is our local minima, and the point 0, 0 is our saddle point. So that's the solution, and see you guys in the next video.